and it also makes me feel nervous because I feel my research is too small and too technical and make big pictures. But you will see what I'm doing for renewable energies. And if you feel we can collaborate, and feel free to contact me. And here is my contact information. So what my research is we develop a high fidelity and high purpose computational framework for renewable energy applications, including wind energy and tidal energy. And for this presentation, I want to introduce you a computational free surface flow modeling technique and its applications to horizontal axis wind turbines. Let me give you some background about tidal energy or hydro energy in the United States. Many people don't know that, hydro energy in the United States is very promising, and we have a huge potential. So here's some statistics from the Department of Energy in the United States. So the length of a U.S. coastline is more than 32,000 kilometers. And then each year, the average tidal wave energy of the United States is around 2,100 terawatt hours. And if we only harness 20% of this amount with 50% conversion efficiency, we can provide 7% of the total U.S. electricity consumption each year. So it is very huge. And in fact, there are lots of development ongoing in the United States. For example, what you see here is a tidal farm deployed by Vanden Power in New York City's Eastern River. However, because I'm a computational scientist, when I look at the literature, I want to see what people are doing in terms of numerical modeling for tidal energy. But if you look at the literature, you will see most of the numerical effort for tidal energy still focus on pure hydrodynamic simulation without considering the effect of free surface. Although many experiments like this one already indicate that the free surface effect can significantly change the tidal turbine performance. So we feel, we need to do something. We develop some method that we can consider free surface in your numerical simulation. So here, let me give you some brief mathematical detail of the method we developed. So in order to model the free surface flow, we utilize the level-set method. So suppose you see a computational fluid domain with a tidal turbine inside, two fluid domains including air and water. So inside of each domain, we define a level-set function phi. And basically, it is a signed distance of each point of the domain with respect to the free surface. And with this level-set function, you can define a heaven-set function. And with the help of the heaven-set function, you can define the fluid velocity, fluid viscosity at each point of this domain by the linear interpolation between the air subdomain and the water subdomain. And once you have fluid properties, and then you can start to write down, Navier-Stokes equation, right, for fluid flow. And here the equations are written in ELE description. Here ELE means arbitrary Lagrangian O'Leary, which is a moving domain technique for solving Navier-Stokes equation. And then for level-set function, we are assuming the free surface is moving with the fluid particles. So as a result, the governing equation for level-set is also a convection equation written in ELE description. And then the question is how to solve those two sets of equations in a fully coupled way. And what we used here is the so-called ELE variational multi-scale formulation. I skipped the derivation of this formulation. I just give you the advantage of the purpose of this technology. Because if you solve a flow past a tidal turbine, the Reynolds number of the fluid flow is very high. So you need a turbulence model. So if you look at this formulation, you will see the first three lines are the standard Galerkin formulation, which you typically see from an element. And then those fine scale terms is acting as a large eddy simulation model for turbulent flow. And there are many advantages of this formulation. So first of all, it is consistent with the strong form equation you just see in the previous slide. And it can handle complex geometry because the geometry of the tidal turbine is very complicated geometry. And it is flexible to different numerical discretizations. You can use finite element, measure-free method, or whatever you want to solve this formulation. And another thing you must include in your formulation for your level set is the so-called reinitialization, because your level set is convected by the velocity. And after you simulate for a while, maybe the signed distance function, a property of the level set field, is no longer preserved. So what we do is after you solve the Navier-Stokes and level set convection equation, we solve another Eklund equation by using this variational multi-scale formulation to recover the signed distance property of the level set field. And then the level set convection and the reinitialization may also destroy your total mass conservation. So to do that, what we do is we perturb your velocity field, your level set field by a global constant, and then we resubstitute into the global mass conservation law such that your total mass is conserved. And this formula is this method is very effective. I mean, among the most of the different techniques, the reason is this is a scalar equation, so it is very easy to solve. And secondly, I mean, we shift the level set field by a global constant. So as a result, you don't destroy your signed distance property you achieved in your initialization. So this is the mathematical approach. And here, let me show you some applications. Before I show you the applications to tidal energy, let me first show you some applications in hydrodynamics. So what you see here is a solitary wave impacting a stationary platform. And here is an experiment conducted by a professor called French at Caltech around 50 years ago. So we compare the normalized time history of those 2 points against the experimental measurement from the experiment. And you can see the computation and the experiment agreed very well. And instead of a stationary platform, I mean, you can do fluid object interaction where the structure is doing rigid body motion. So what you see here is a free surface modeling of a planing vessel. And this figure shows you the final configuration of the vessel and the corresponding wake pattern behind it. And there is an experiment in the literature, and you can see we are able to reproduce the wake pattern very well. And we also compare the trim angle of this boat in the fully developed stage. As you can see, the fully developed stage computation and experiment almost reproduced the same number. But if you want to apply this methodology to tidal turbine, you still have one issue. The issue is you have a tower, which is stationary, and then you have a rotor, which is spinning. So in your computational fluid dynamics simulation, if you are using a single conforming fluid mesh for the entire fluid domain, and then within several steps, your mesh will be distorted if you are familiar with finite elements. So as a result, what we do is we decompose the fluid domain into 2 parts. One part contains the spinning rotor, and one part contains the stationary tower. And we utilize this so-called sliding interface technique to make sure that even you have a non-matching sliding interface between the rotor subdomain and the tower subdomain, your fluid solution, including velocity, level set, and traction, are still continuous across this interface. So with this technique, you are ready to go. So I think we are the first few people to investigate the free surface effect over 4 tidal turbine machines, including both tower and the rotor, in free surface flow. So we investigate the effect by first using a uniform inflow condition. We performed pure hydrodynamic simulation without free surface effect, and we also compute free surface simulation. We also do free surface simulation with 2 different deep immersion depths. I mean, those immersion depths are from the experiment I showed you before. So this is the most important results. Those 2 figures shows you the thrust coefficient and the production coefficient for all the simulations. Here are some important information I want to emphasize. So first of all, free surface computation agree very well with the experiment for both deep immersion case and shallow immersion case, as you can see here. And secondly, pure hydrodynamic simulation is not accurate. This is what I'm trying to say. If you immerse your turbine very deep, it is fine. But if you immerse your turbine very shallow, and then you can clearly see the discrepancy between the simulation and the computation. And thirdly, what we found is the performance of the tidal turbine is better in deep immersion case. And of course, instead of uniform inflow condition, you can put some waves. So this is a free surface simulation of this tidal turbine subject to airway wave inflow condition. And you can see in this case, the flow behavior is much more complicated. And you see a lot of tip vortex generated by the rotation of the rotor. And you also see the strong interaction between the free surface and the tip vorticity. So because you have wave, as a result, you will see much fluctuations for the thrust coefficient and the power coefficient. However, if you average the coefficients in the fully developed stage, you still see that as you place your turbine closer to the free surface, the coefficients the coefficients will decrease. And this means free surface has a negative effect on the tidal turbine performance in those idealized inflow conditions. What I mean by idealized, I mean uniform inflow or airway wave inflow, because in reality, there's no such a flow condition, right? This conclusion is not surprising, but my point is you have to quantify it, right? How much is the effect? And also, what if the turbine is in realistic wave condition? So in order to answer those questions, I think you have to consider free surface in your numerical modeling. And also, this is just a single turbine. What will happen in a tidal form? So what we do here is we simulate two back-to-back tidal turbines in free surface flow subject to uniform inflow condition. And the deep immersion case we choose is the deep immersion case I just showed you in previous slide. Because what we see is in deep immersion case, the tidal turbine is not affected by the free surface. But if we have two turbines back-to-back, what will happen? So we did a free surface simulation, as you can see here, and we also did pure hydrodynamic simulation. So this snapshot shows you the average velocity magnitude in certain locations between the front turbine and the back turbine. And as you can see, in the free surface simulation, the velocity magnitude is lower compared with the pure hydrodynamic simulation. So, which means pure hydrodynamic simulation overestimates the velocity magnitude in the wake. So, and this will affect your results. So this figure shows you the time history of the thrust and the power coefficient for the front turbine and the back turbine. And as you can see, for the front turbine, the computational results still agree with the experimental measurement. But for the back turbine, since it is affected by the wake, right? So you see huge reduction in terms of thrust coefficient and the power coefficient. And this is the simulation for free surface. And when you compare the averaged coefficient, you will see that in terms of thrust coefficient, we see 70% reduction for the back turbine. And in terms of power coefficient, you see 30% reduction. And when we compare pure hydrodynamics and the free surface simulation, as you can see, for the front turbine, pure hydrodynamic simulation is still okay. But for the back turbine, as you can see, pure hydrodynamic simulation overestimates the coefficient, right? Which is very significant as you can see from the plot. So with this, I want to draw my conclusion. So what I want to show here is we introduce you a validated computational free surface flow formulation, and we applied to tidal energy. And using this computational framework, you are able to investigate the free surface effect on tidal turbine, and you are also able to investigate the wake effect when you simulate an entire tidal form. And the last thing I want to say is we are writing our own code, and it is very general and very flexible. And you can definitely apply to other hydro energy problems where free surface flow or safety plays an important role. So with that, I thank you for your attention.
Okay, thank you. After the
Yes.
Yes.
In one of your simulations, you're showing this RPM at the speed. So what's the RPM of those turbine you're running at? Because it is, I mean,
Oh yeah, you mean the rotational speed, right?
rotational, yeah.
It is compared with wind turbine, it is very fast because it's the rotor diameter is only 0.8 meter, so the RPM is 28.6 rad per second.
Well, I mean, the RPM of the MHK devices normally are 3-4 RPMs. I mean, they're very slow in moving into the water.
You mean the tidal turbine?
The tidal turbine.
I mean, for this application, what we the model we adopt is let me show you the original design. Is from this person in UK, and they have done a lot of experiments. I mean, the RPM changed from very slow to very high, and what we pick up to validate our computational method is 28.6. Yes. Okay. Thanks.
So what's the LES model here?
LES model is a so-called variational multi-scale formulation. So the idea I didn't say is I can give you a little bit of details. So the model is you decompose your velocity field, pressure field, and the velocity field into two parts. And then the coarse scales are resolved by your given problem mesh. And then the fine scales are need to be modeled, and depending on your LES model, right? And then VMS, I mean variational multi-scale formulation, is you model the fine scale to be proportional to your strong form residuals of your Gaussian equation, and then you resubstitute those residuals back into your Gaussian formulation, and you will get this. And we have validated this method by simulating a bunch of benchmark problems. The accuracy is very nice. It is reliable.
Do you need a one model?
No, we don't need any additional model. So those terms are acting as a LES model. So if you refine your mesh very fine, if your mesh is very fine and your delta t is very small, those terms will become zero. So it is a direct numerical simulation. Thanks.
Any further question? If not, we thank Jinghui.
Okay, thank you very much.